Our AI model just made a terrible mistake. It predicted something and got it completely wrong. But here is the crazy part. It knows exactly how wrong it was. Hi, I'm Tiyasa, an AI engineer, and by end of this video, you will understand how AI measures its mistakes and why that's the secret behind how it learns anything. Every neural network does one thing, it makes predictions. But a prediction alone is useless because the real question is, was it correct or how wrong was it? If the model does not know it made a mistake, it has no way to improve it. That's where loss functions come in. A loss function is simply a way to measure how bad was the prediction. Let's say we give the network an input 4, 5. It processes this through its hidden layers and predicts 0 0.1. But the correct answer was 1. That's not a small mistake. So now we calculate the loss, the gap between the prediction and the reality. Big gap means high loss and small gap refers to low loss. This number is what tells the network you are very wrong, fix this. But real AI does not learn from just one example. It learns from thousands, sometimes millions of examples. So instead of looking at one mistake, we calculate the average loss across all examples. This is called empirical loss. Think of it like this. One bad answer does not matter much, but if your average score is bad, then your model is actually performing poorly. So, the goal of training is simple. Minimize the average loss. Now, let's look at a specific type of problem called binary classification. When you have two classes like yes or no, 0 or 1, true or false, and the model outputs a probability between 0 and 1. Now imagine this. The model predicts 0 0.1 whereas the correct answer is 1. So, it was confidently wrong. And we punish confidence in this wrong direction. This is exactly what binary cross entropy does. You don't need to memorize a formula. Just remember, the more confident and wrong the prediction is, the higher the loss. Now, what if there are more than two categories? For example, recognize handwritten digits. Now the model outputs a probability for each class. Let's say the correct answer is digit 5 and the model assigns probability 0.91 to digit 5, which is higher than other digits. That's pretty good, but not perfect. There is still uncertainty, and training is all about reducing that. So, we use categorical cross entropy. Here is the key idea. We only care about one thing. How much probability did the model give to the correct class? So, high probability means low loss, and low probability means high loss. Before this step, one important process happens. The model produces logits. Then softmax converts them into probabilities. Then the loss is calculated. So far, we talked about classification. Now, let's talk about regression. This is when the model predicts continuous numbers. For example, house prices, exam scores. Let's say actual grade of a student is 90, but the model predicted it as 30. So, the error is 60. Now, here is the key idea. We squared the error. So, 60 squares become 3600. Why? Because big mistakes should be punished much more than the small ones. If error is 1, then the loss is 1. If the error is 60 in our case, the loss is 3600. Then we take the average across all the examples. That's the mean squared error or MSE. Lower MSE means better predictions. Let's quickly connect everything. So neural networks make predictions, loss functions measure the mistakes, training reduces that loss, so lower loss means better model. That's the core idea behind learning in neural networks. But now comes the most important question. Knowing the mistake is one thing, but how does the model actually fix it? How does it know which bits to change? And by how much? That's where gradient descent comes in. And that's exactly what we'll break down in the next video. If you found this video helpful, please like, share it with your friends, and subscribe to my channel. And let me know what you want to learn next in the comment section. See you in the next video. Till then, goodbye and happy learning.